In the mid-60s, two researchers, Atkinson and Schifrin, proposed a model called the Information Processing Model, or IPM. This model uses a computer analogy to explain how the brain manages information when we learn. Even though our brains don't work exactly like computers, this model is helpful for understanding the brain's learning process. Computers have many parts that help them function, but we will look at the basic components that apply to our brain analogy. Input devices, such as a mouse, keyboard, or camera, collect information and transfer it to the computer's processing unit. In the processing unit, this information is coded and manipulated in various ways as short-term memory, sometimes called RAM. Here, information is processed rapidly using programs stored in the computer. This is the part of the computer where thinking occurs. After processing occurs, the information is moved to the hard drive for long-term storage, where it becomes available to be used later for more processing or as output from the computer in the form of text, graphics, sound, calculations, or videos. Atkinson and Schifrin's information processing model proposes that, as learning occurs, the brain works in ways similar to a computer. Information enters the brain as input from the learning environment, in this case, the classroom. Information is received into sensory memory and immediately transferred to working memory. This is where processing occurs, much like the short term memory of a computer. After information is processed in working memory, it is transferred to a long term memory for storage. This is the hard drive of the brain. Information goes back and forth from working memory to long term memory as it is processed in new ways. This is where learning occurs. The output in this model is any learning behavior students exhibit, such as reading, writing, speaking, problem solving, or actions they take as a result of their learning. Let's take a closer look at the process that occurs in each of these components. Students receive a lot of information in the classroom. It might be information intentionally presented through classroom experiences, but it can also be anything that is present in the environment. In either case, students use their senses to become aware of these stimuli. All of it is transferred into sensory memory, which holds unlimited amounts of information at any given time because stimuli in the environment constantly bombard us. However, sensory memory holds information in the brain for only a few seconds or less. Consequently, most of the information we receive from our environment is immediately forgotten and discarded from our sensory memory. The only thing we retain is the information we choose to pay attention to, which is relatively quite small. We might pay attention to something for various reasons, because it's exciting, loud, colorful, interesting, important, or even because somebody told us to. That information is then transferred to working memory. You might also hear this called short-term memory. Educational psychologists use the term working memory because this is where information is processed to create new knowledge. In order for students to learn, their working memory must cooperate with long-term memory. Long-term memory is just what it sounds like. It's where all the information we've collected and processed is stored. When we learn, our working memory retrieves related or relevant information stored in long-term memory and integrates it with the new information we receive from sensory memory. These pieces of information are processed together and reconstructed to create new learning. In a process that is sometimes called elaboration or elaborative rehearsal, information remains in the working memory only for the short time it takes to manipulate it into newly constructed knowledge. This new knowledge is immediately transferred into long-term memory for storage and subsequent retrieval. So, in essence, learning is the construction of knowledge by combining our prior understanding with new information. You may be familiar with schema theory, as proposed by Jean Piaget in the 1950s. This earlier model is consistent in many ways with the information processing model. The theory describes schemas, which are organized chunks of information that form an idea or a concept. Schemas are stored in long-term memory. Every time we use our working memory, we process new information from sensory memory with related schemas retrieved from long-term memory to create bigger and more complex schema networks. The modified schemas are then transferred back to long-term memory. In this way, our conceptual understanding grows. This provides our brain with the means to solve increasingly complex problems and use higher level reasoning. Cognitive scientists use the information processing model to help understand and explain mental processes. They have found that different types of memory have different capacities and storage durations, as seen in this chart. This has implications for the type of environment and instruction that teachers need to provide to create optimal learning experiences for students. Attention is an important part of the teaching and learning process because of the short duration and large capacity of sensory memory. As teachers, we must help our students attend to the key points of the concepts we are presenting through careful design of learning experiences and environments. We are competing for their attention with a lot of other stimuli. Working memory holds only a small amount of information and can be retained for only 5 to 20 seconds. This time can be extended by providing cues and connections to students' prior knowledge, as well as scaffolds that help students make connections to increase the depth of elaboration. The more you use new knowledge, the more complex the new schema you transfer to long term memory will be. Many researchers believe long term memory has unlimited capacity and that anything stored there is permanent. They hypothesize the reason we forget things is that discrete pieces of stored information cannot be retrieved because they are not connected to other pieces of information in more complex schemas or networks. Unconnected pieces of information cannot easily be retrieved. This is why it's important for students to construct knowledge through elaboration rather than simply trying to memorize new information. To better understand the importance of networks of ideas in the brain, it is important to know the brain is not simply three separate areas of memory that transfer information back and forth like a computer. Rather, it is a big ball of nerve cells called neurons that constantly change by making connections with one another. These connections form the theoretical schema in our model. This graphic is a model that represents a neural network in the brain. The little dots are neurons, and these are the connectors between them. The more connections there are, the bigger these dots get as those brain pathways become much richer, deeper, and more complex. Conversely, if your brain tries to retrieve a tiny piece of disconnected information like the one up here, it probably won't happen because it's isolated. So, the more your information is connected to schema or bigger ideas and concepts, the greater will be your ability to learn by connecting new ideas with prior knowledge. That is the information processing model in a nutshell.